Welcome to module number 2 in our series on artificial intelligence. This one addresses artificial neural networks specifically as a framework to which machine learning may be applied. In the first module, we introduced several concepts related to artificial intelligence, such as neural networks and machine learning, and we provide some essential definitions that we're going to use in this and later modules. In this module, I'm trying something new. I'm going to begin with what I'm calling a plain language discussion of our topic, which in this case is artificial neural networks. For those of you that are familiar with the website Reddit, this is sort of like the ELI 5. We're going to explain the topic like year 5, and then after this, we'll return to a more normal or more advanced discussion of the topic. So a neural network is a connection of simple units called neurons, and sometimes we'll refer to them as nodes. Each node or each neuron represents the simplified behavior of a real neuron in our brain. Now, I should preface this by saying it's very simplified. Each neuron or node performs 4 tasks, more or less. It accepts scalar input values from other neurons or from the environment potentially. It multiplies each scalar input by a coefficient that we refer to as its synapse weight. It sums those scaled values together to yield one that we refer to as h. We also call that the weighted sum. And then it applies some function, we call it an activation function, to that weighted sum. In short, each neuron accepts several values and generates one value output. And so here we have a very basic schematic of a neuron. I'm going to come back to this later. But in short, we can see we have 3 inputs coming in. We have 3 coefficients. They are multiplied, scaling those inputs. We then sum those together. We apply an activation function, and we generate an output. So keep this in mind. We're going to come back to this figure. There are many different activation functions that may be used in artificial intelligence. One common activation function is the unit step. And for that, if the weighted sum, which we called h previously, is greater than some threshold, it generates a 1. If that weighted sum is less than some threshold, it generates a 0. So it looks a lot like this. The activation function, whether it's unit step or something else, defines how a neural network processes inputs and generates outputs. The most basic neural network structure is feed-forward, where inputs are observed, pass through one or more layers of neurons, and then one or more outputs are generated. Ideally, that output or those outputs match the behavior of some complex system that we're trying to approximate. So one example could be recognizing someone's face. Before training, however, this will not be the case. It would be highly unlikely for a neural network before being trained just randomly by chance to match the behavior of some complex system. We use machine learning to teach our neural network how to perform some desired task. This requires us to give the neural network training data. That includes inputs along with known ideal outputs. And then we vary the synapse weights. Remember, those are the coefficients of the inputs until it acts in the desired way, or the way that we want it to. Just like learning to shoot a free throw, we can keep changing our method until we consistently achieve our goal, which in that case would be making a basket. Let's say our neural network generates a value that's too high as compared to the ideal. We can reduce some of the synapse weights. If the neural network generates a value that's too small, too low, as compared to the ideal value, we can increase some of the synapse weights. Machine learning is inherently an iterative process. There are many interesting artificial neural network types or characteristics that artificial neural networks can have. A deep learning neural network is one that uses lots of neurons and lots of layers to mimic complex patterns. A convolutional neural network extracts features, could be from an image, to simplify the inputs coming into the neural network. Transformers analyze strings of data like text or audio, and general adversarial networks are tasked with creating new things like pictures based on previous observations. In short, a neural network is simply a network of simple nodes that can be trained to mimic complex patterns or make complex decisions. So that concludes the plain language discussion section, or the section where we're going to explain it like we're 5. And now we're going to move on to a more advanced discussion of artificial neural networks. The story of artificial neural networks begins with the McCulloch-Pitts neuron model. So the concept of an artificial neural network was first proposed by Warren McCulloch and Walter Pitts in 1943 in a technical paper. Their objective was to understand how an interconnection of generic computational blocks may facilitate learning and be used to solve more complex problems. In that work, they defined the McCullough-Pitts neuron model, which employed a unit step activation function, and down here we can see the equation, which we're going to go through in more detail in a second. Essentially, we see that some output is generated when we apply the unit step activation function to the weighted sum, the product of the synapse weights W and the inputs X, minus some bias offset. So let's spend some time explaining how this equation, as well as the McCullough-Pitts neuron that it describes, how both of those work. We're going to start from the left with the variable y subscript calc. So y subscript calc represents the output generated by a neuron or calculated by a neuron, and we can contrast that with y ideal, which represents the ideal desired output of that neuron as indicated by the supplied training data. Equivalent to y subscript calc is x superscript m, where x is merely a state within the neural network, and m indicates which neuron generates that state. So you can see here that this variable is useful when we're talking about a single neuron. However, when we have a network, an interconnection of multiple neurons, it's generally going to be important for us to keep track of which state is associated with which neuron or was generated by which neuron. So how do we generate this output? We apply some activation function to a weighted sum, which we refer to as h, and then over here, what we do is we expand h. Everything inside of these parentheses is contained within h. So we see h may be split up into two parts, one minus the other. So on the left-hand side, what we have is the sum of all the inputs in the system, because all of them may be connected to our neuron, times their respective synapse weight. So let's draw a little picture to explain this. Let's say we have the outputs of three neurons, which we call x1, x2, and x3. And then over here, we have some neuron, which I'm calling n5. Okay, so m equals 5 for this. Let's assume that all three of these do have some connection. How would we index the synapse weight that links x1 to n5? The subscript always contains the origin. So the origin of this connection is 1, and the destination is 5. Down here, subscript would be 3, superscript would be 5. And so that helps us understand how this weighted sum works, right? We are looking at all the states generated by all the neurons from 1 to n sub x, and we are scaling them by the synapse weight, which is described by its origin as well as its destination. Now, in reality, this will not contain the output generated by all neurons because some of these synapse weights are going to be 0, indicating that there is no connection. Now, we subtract from that weighted sum a bias offset indicated by b sub 0, where m indicates which neuron we're talking about. So this gives us a pretty good description of how the McCullough-Pitts neuron works. And for the McCullough-Pitts neuron specifically, we would be using a unit step function here as our activation function. So there is one equivalency that we're going to use throughout this module, and I wanted to take a quick second to state it. Whenever we see this symbol gamma sub wx with an index of m, that's really just this weighted sum right here. For some of the equations, it can be a little bit long to write this whole summed portion, and so we're going to use this gamma sub wx as a shorthand for it. And you can see that these indices cancel out, so we really only have a need to indicate the destination index m. Okay, so let's talk more about the activation function. The activation function calculates the output of a neuron or a node based on the weighted sum of its inputs as well as the bias offset, which we call b sub 0. Right, we see that this value, we've talked about it several times before, it's h, right, is equal to the weighted sum of all of the states in the system times its respective synapse weights, minus the offset, the bias offset for that specific neuron. And here, I apologize, I switched from C to gamma. Here we have gamma sub wx with a superscript of m, minus b sub 0 with a superscript of m. And so our activation function is applied to that. The key roles of an activation function include nonlinearity. The activation function introduces nonlinearity to the input-output mapping of the neuron, or that input-output relationship. Differentiability. This activation function is generally defined to facilitate calculation of gradients or derivatives, which is essential to machine learning and the back propagation algorithm that it employs, as well as controlling the output. So the activation function defines the minimum and the maximum of the output that the neuron can generate. One popular modern function, more modern than the unit step, is the rectified linear unit, which we are going to discuss in later modules. So here we have an example of a McCullough-Pitts neuron with a unit step activation function. I don't think there's a need for me to discuss this equation again. The state generated by the mth neuron, right? This is generated by applying an activation function, which in this case is the unit step. We apply it to the weighted sum minus the bias offset. Now there's two cases if we're discussing a unit step function. There's the case where everything in here, which we refer to as h, right? If that's greater than or equal to 0, then we end up with a value of 1. If it's less than 0, then we end up with a value of 0. And so that's all we're really saying right here. A value of 1 is generated by the McCullough-Pitts neuron if the weighted sum is greater than the bias offset. It's equal to 0, or it generates a 0 if the weighted sum is less than the bias offset. And so up here, we can see a visual representation of that input-output relationship. And what we see is that on the x-axis, we have the value of gamma. And then here we have the offset b0. So once gamma equals b0, we flip from a 0 to a 1. And this may be referred to as a binary classifier or a basic perceptron. So this figure may look familiar. We used it during our plain language discussion. It expands upon our definition of the McCullough-Pitts neuron, and so we can look at the individual pieces. So here we have 3 inputs that are being supplied to our neuron, and associated with it are 3 different synapse weights. The indices are appropriate, right, because the origin of the first input is 1, the origin of the second input is 2, and the origin of the third input is 3. The destination of all of them is the same, neuron M, so they all have the same superscript. So we multiply each input by its corresponding synapse weight. We then supply all 3 of those values to our summer. We can't forget to subtract out the offset bias, denoted by b sub 0. This creates the value that we refer to as h. We then supply that value to our activation function, and that spits out a value that we can refer to as y sub calc, or we can refer to as x superscript m. And we've already taken a look at this visual representation of how the unit step function works. Next, let's discuss some common activation functions. We're going to begin with the unit step. Before we do that, however, let's discuss these graphs in a little bit more detail. For all 3, the horizontal axis is defined in terms of gamma subscript wx. You may remember that's equal to the weighted sum of the synapse weights and the inputs going into a given node, and this represents at least part of the input to the activation function. The vertical axis represents the output that this activation function generates, which we can denote as y or as x superscript m, again assuming that we're dealing with the mth neuron. For all 3 of these, we'll see that the dotted blue line indicates where the bias offset threshold lies, as denoted by b sub 0 superscript m, again to indicate this is for the nth neuron. Then we also have the green line, which defines the boundary of a window. So what you can see here is we have the blue line, which represents b sub 0, and then we have over here b sub 0 plus delta, and you could also on the other side define a b sub 0 minus delta, and so that's useful for some of these other functions. Now let's return to the unit step activation function. This is one we've discussed several times before. But again, what we see is that the unit step activation function generates a value of 1 when the weighted sum of the synapse weights and inputs is greater than the bias offset. So that would be essentially this side over here. And it generates a 0 when that value, what we've been calling gamma subscript wx, when that's less than b sub 0, we end up with a value of 0. So that's the unit step activation function. Next, we discuss a piecewise activation function, which, unlike the unit step, has 3 regions along the x-axis instead of 2. So the midpoint for this activation function is defined by the offset bias b sub 0. We have the high end of this window, which is defined as b sub 0 plus delta, where delta is going to be user-defined. And then we have the low end of this window, which is defined as b sub 0 minus delta. So the width of this window would be equal to 2 times delta. And so we have 3 different regions. Okay, we have region 1, where gamma subscript wx is less than b sub 0 minus delta. We have the second region, which is in the middle here. And then we have the third region, which is essentially to the right, when gamma subscript wx is greater than b sub 0 plus delta. Okay, so let's talk about what happens in the first region. Essentially, when we're over here, the weighted sum of the synapse weights and inputs will be less than or equal to b sub 0 minus m, and for that we end up with an output of 0. So that's region 1. Let's skip over to region 3 for a second. I apologize, there's a mistake. This should be greater than or equal to. So essentially, when the weighted sum of the synapse weights and inputs is greater than the threshold plus delta, meaning we're to the right here in the third region, we end up with an output of 1. Okay, and in the middle, in this region right here, we end up with this linear slope, which is defined by the linear equation 1 over delta times gamma wx minus b sub 0 plus 1/2. The third activation function is the sigmoid activation function. It uses a similar offset bias threshold and window as defined for the other two. As you can see, the shape of this function resembles the piecewise. It's essentially the piecewise with some rounded off corners, and its behavior is defined by this expression below. Next, let's discuss some artificial neural network topologies. The simplest is a single layer network. That's one with only one layer of neurons between the input and the output. The input layer is that which accepts the inputs, and the output layer is that which generates a desired input. For a single layer network, what we can do is that assume this single layer fills the role of both the input and the output layers. Next, we have a multi-layer network, and that is one with multiple layers between the input and output, or multiple hidden layers between the input and the output. And so we could adapt our drawing up above to look like this, where now we have essentially an input layer, we have an output layer, and then we have 3 hidden layers, right? Again, a hidden layer is one that is internal to the neural network such that it does not directly interface with the system's input or output. So here we have 5 layers. We have our input layer, we have our output layer, and then we have 3 hidden layers. A feed-forward network is one with no loops, where all the states propagate from the input layer to the output. So here we have an example of a feed-forward topology, right? Everything is moving forward. And then we could have a looped or feedback topology where you have something that looks like this. You have outputs that can be looping back on themselves. Here we have a visual representation of our feed-forward network. The input layer is shown in yellow, the output layer is shown in red, and we have 3 hidden layers shown in blue. And if we assume that all of these connections are unidirectional, then that by definition makes this a feed-forward multi-layer neural network. The binary classifier is an important and fundamental type of artificial neural network, one that can be used to address a number of really important problems with yes or no answers. Let's say, for example, your iPhone is trying to determine whether the person looking at it is its owner, whether it should yes or no unlock the operating system, and that could fall under the category of a binary classifier. So it's an algorithm or neural network structure that's tasked with classifying the elements of a set into one of 2 groups, and another example could be a positive or negative medical diagnosis. Now we can actually subdivide these positive and negatives 2 categories into 4, because we have the case where the artificial neural network tells us that the result is positive and it is actually positive, so that would be true positive. We have the case where the neural network tells us that it's positive but it's actually negative, so we have a false positive. Then we have the case where the neural network tells us that it is negative, but it's actually positive, false negative, and then true negative. So essentially, right, we have 2 cases where true positive and true negative, where the answer is correct, and then false positive and false negative is when the neural network is generating an incorrect answer. So I just wanted to make us familiar with that terminology. What's a perceptron? A perceptron is an algorithm or neural network designed to mimic the binary classifier behavior via learning, and it was first proposed by Frank Rosenblatt in 1957. So what he saw was that a single layer perceptron can only distinguish between what we call linearly separable patterns. And over here, I have a picture of the Mark I perceptron hardware from 1960 that was built, but unfortunately had pretty limited success. So let's take a look at linearly separable patterns. Like we said before, the performance of a single layer perceptron can improve with more data samples. However, it can never progress beyond linear separation or flat planar separation for higher dimensional problems. So what does this figure over here tell us? We have an example of a binary classifier where on the x-axis and y-axis we have 2 characteristics, domestication and size, and then you can see here we have examples of dogs and cats. Now, as we provide more samples, we can see that the slope of this line becomes adjusted in order to better separate the dogs from the cats. However, it's ultimately limited by this linear separation and would be unable, for example, to separate between a cat and a dog if we had one example of a cat being here deep on the quote-unquote dog side. Next, let's discuss some interesting neural network characteristics or types of neural networks. The first is a deep learning neural network. It employs a relatively large number of discrete stages, each with a relatively large number of hidden layers and relatively large number of neurons. Now, this structure facilitates highly complex pattern recognition. Stacking too many layers, greater than 50 more or less, previously resulted in what we call the degradation problem, where we had reduced training accuracy. Recent technological advances, however, have alleviated this problem with many neural networks, one example being transformers, regularly and effectively using more than 100 or more than 1,000 layers. We also have a convolutional neural network, and that's one that employs a convolutional layer to extract features from data, such as an object from an image or an attribute from an image. One example could be a nose or an eye. Now, this is achieved by calculating the convolution or cross-correlation of various data subsets, aka sub-images within the main image, and a variety of predefined and often randomly generated filters. Another interesting neural network type is the transformer. We talked about it a second ago. And this type of neural network is designed to predict sequential behavior in data, examples being text or audio, anything that can be represented as a time series. And this is the basis for natural language processing. Another interesting type, one that's especially interesting now, that would be the general adversarial network. And this is a neural network designed to generate new data that resembles that supplied to it during training. It consists of two neural networks, the generator and the discriminator, which compete against one another within a game theoretic framework. And this is the basis for software like Sora or DALL-E that are able to generate new videos or new images based on lessons learned from the training data. Now, obviously, this is just a few examples of interesting neural network types and characteristics, and we're going to dive into some others later on as well. So that marks the end of this second artificial intelligence module. We further discussed the topic of artificial neural networks with focus on the McCullough-Pitts neuron model, the role of synapse weights and activation functions in a neural network. We provided a comparison of feed-forward and feedback network structures, and we also covered many basic artificial neural network characteristics or types, with one example being the transformer. In the next module, module number 3, we are going to focus on machine learning, as well as using Python and the PyTorch library to practically train a small neural network.